Hello students, happy morning. Class 12 Physics Unit 1 Electrostatics Revision continuation video. In our previous class we discussed the book bag question from the subtopic Gauss law and its application. Here one more question is pending that we see by today, that is obtain the expression for electric field due to an uniformly charged spherical shell. Okay, we need to find the electric field due to an uniformly charged spherical shell. Okay, for that I consider a uniformly charged spherical shell of radius r and the charge in the shell will be q. Okay, we need to find the electric field for three cases. In first case, the electric field at the point outside the shell. Okay, so we are considering the point P at a distance small r from the center of the spherical shell. Okay, this distance is greater than the radius of the spherical shell. Okay, for this case, first of all I consider a spherical shell of radius capital R. Here q is a charge that is distributed on the surface of the shell. Okay, at the center point of the shell at a distance r, the point P is plotted. At that point I draw a Gaussian spherical surface. Okay, on that surface we need to find the electric flux, so I am applying Gauss law. Okay, we know Gauss law, that is phi is equal to q n plus by epsilon. We know phi is equal to E vector dot dA vector. Okay, here E vector is a electric field that going outwards, because here we are considering the charge q is greater than 0, that means positive charge. Okay, so further the electric field E vector is going outwards. Okay, at the same time on the Gaussian surface the electric field value will be same. Okay, because it is spherical symmetry, so the electric field on that each and every point on the Gaussian surface, that is spherical surface, will be same. Okay, and the area vector and the electric field vector are in same axis, so the angle between the E vector and dA vector will be 0. Okay, so on simplifying this we get closed interval of E dA is equal to q enclosed by epsilon naught. Okay, because cos 0 became 1, that is E dA. I already told the electric field is uniform or constant at the surface, so we are taking the electric field out of the integral. Okay, then dA, integrating dA, that is a spherical Gaussian surface, so integrating this we get surface area of the sphere, that is 4 pi r square. Okay, we need the electric field alone, then E is equal to q by 4 pi epsilon naught r square. Okay, in order to write in vector form we can write E vector is equal to q by 4 pi epsilon naught r square r cap. Okay, see here we are considering the positive charge. If suppose we are considered as a negative charge, then q is less than 0, then electric field is inwards. Okay, then next case, that is at the point on the surface of the spherical shell, electric field at the point on the surface of the spherical shell. Okay, for this case we are considering the point P on the surface of the spherical shell. At that case r, small r is equal to capital R, so the equation became E vector is equal to q by 4 pi epsilon naught r square into r cap. Okay, then the third case, electric field at the point inside the spherical shell. Okay, we are going inside the spherical shell. Okay, this is the spherical shell having the radius capital R. Inside that we are plotting the point P at the radius r. Okay, then we draw a Gaussian surface, but this Gaussian surface does not have any charge distribution. Okay, so for that the electric field will be 0 for this. Okay, see the electric field due to the uniformly charged spherical shell is 0 at all point inside the shell. Okay, then there is a graph. This graph represents the variation of electric field with the distance. Okay, see in this range, that is this graph is between electric field and distance. Okay, inside the charged spherical shell the electric field will be 0. Okay, but outside the shell there will be electric field, but the distance increases, the electric field will be decreases. Okay, let me see what are the important things needed to answer this question. Okay, first of all we have to consider a charged spherical shell. Okay, of radius capital R. On that shell q is a charge that is distributed on on it. Okay, let we see the first case. In first case, R is greater than R, that is we need to find electric field at a point outside the shell. Okay, at a point outside the shell. Okay, for this we need to draw a diagram. That is this is a spherical shell. I am plotting a point P at a distance r from the center of the spherical shell. Then this surface is known as Gaussian surface. Okay, for that surface we are applying Gauss law. We know Gauss law, the closed rule of E vector dot dA vector, that is flux is equal to Q enclosed by epsilon naught. Okay, then closed rule of E dA cos theta is equal to Q enclosed by epsilon naught. Okay, here cos theta is an angle between E vector and dA vector. Here if suppose I am consider this charge as a positive charge, so electric field is going outwards. Okay, at that point the area vector is in the direction of the electric field, so E vector and dA vector are in the same direction, so theta will be 0 degree. Then cos 0 became 1. Then closed rule of E dA is equal to Q enclosed by epsilon naught. Okay, here on that Gaussian surface electric field will be uniform, so taking out of the integral, closed rule of dA is equal to Q enclosed by epsilon naught. Okay, here integrating a small area on the sphere, we get the surface area of the sphere. Okay, we get 4 pi r square, that is equal to Q by epsilon naught. We need electric field around E is equal to Q by 4 pi epsilon naught r square. Okay, this is the expression for electric field at a point outside the spherical shell. Okay, the next second case, R is equal to R, that means electric field at the point on the surface of the spherical shell. Electric field at a point on the surface of spherical shell. Okay, we need to find here alone. Okay, for this we need to draw a diagram. This is a spherical shell of radius r. We need to find electric field here. For this case, R is equal to R, then the electric field is equal to Q by 4 pi epsilon naught capital R square. Okay, then last case, that is case 3, R is less than capital R. That means we need to find electric field at a point outside the spherical shell, sorry, at a point inside the spherical shell. Okay, for this we have to draw a diagram. This is a spherical shell of radius r. We are considering one more Gaussian surface having the radius r. Okay, here we know all the charges are present on the surface of the spherical shell. Okay, not inside the shell. So by applying Gauss law, we know closed rule of E vector dot dA vector is equal to Q enclosed by epsilon naught. After solving this, we get E dA is equal to Q enclosed by epsilon naught. Again solving this, we get E 4 pi r square is equal to Q enclosed by epsilon naught. Here this Gaussian surface, okay, this is a Gaussian surface. This Gaussian surface does not having any charge. Okay, it does not enclose any charge, so Q enclosed becomes 0. Okay, then electric field is 0. Electric field inside the conductor will be 0. Okay.